Thank you very much for the invitation. I'd just like to say that I can see the chat here, so feel free to bother me during the talk so that I can make comments if necessary. And let me go through my first slide. So when I received the invitation for this talk, it was quite challenging for me to decide on what I was going to talk, because well, the community is a wind energy HPC community, right? And I come from an atmospheric modeling community. But then I realized that most of you guys need this for, well, to actually run your simulations. You actually need the atmospheric modeling community as well. But you are users of this community, right? And I'm working on the development on this community. So what I thought of doing here for this talk is more of an introductory talk where I show a little bit of the history of weather and climate modeling and some challenges. And why is that? Because, well, this is mainly guided by HPC reasoning. So I thought it would fit well this community. And one of the other reasons is that this motivates the reason why we're going towards MPAS, and people in this community are going towards MPAS. So why MPAS? That's one of the things. And then I want to discuss, well, how is MPAS with respect to HPC, right? And some ideas with respect to MPAS for wind energy modeling, and that's more or less what I want to talk here. Okay, there's a big disclaimer here. So I'm not part of the MPAS developers team. So I've worked. I know Bill Skamrock. I know some of the developers. I've worked with some of the guys that developed the dynamical core of the atmospheric model MPAS, and I've worked for 10 years on numerics on that. But I'm not part of any of the official NCAR developers team. Okay, so this is just a disclaimer here. Okay, so let's go ahead. And okay, so first things, let's get straight to, well, where are we gonna what are we gonna discuss? So we're gonna discuss what's called geophysical fluid dynamics, right? You're mostly aware of computational fluid dynamics in general, based on three-dimensional Navier-Stokes equation. Well, here we're interested in usually simplified models, okay? And it depends on what you want to investigate. You will be on this line. And this already gives two-dimensional barotropic equations from here, sorry, already gives some good insights for the atmosphere. And then you can go up all the way to three-dimensional Navier-Stokes equation. One thing that's very important to keep in mind is that the atmosphere is fully coupled globally, right? So you can work on a regional model, but then you'll have to couple it with some kind of boundary so that you get the fully global coupling. So we're usually not there yet on a three-dimensional Navier-Stokes equation. We will see that we are mostly on a primitive equation, which is a set of hydrostatic assumptions. So you made an assumption about the vertical dynamics, or on non-hydrostatic models. I'll just get onto that in a minute, okay? So this is our setting. We'll be working mainly on these two sets of equations, but some of the results might be, I'll make comments on shallow water equations as well. So this is what happens, and this is our main goal, right? So at the moment, most atmospheric models run, global atmospheric models run what's called the hydrostatic equations. And the issue is that this setting is inadequate for resolutions that are very high, right? So it works well for up to 20 or 10 kilometers of horizontal resolution, but it doesn't work well if you go towards convection resolving scales of around 10 kilometers or less. So for this kind of resolution, you need to use compressible Euler equations, right? And this is the common setting of these equations, those three-dimensional momentum equation, continuity equation, thermodynamics. And you're going to couple this with a set of additional variables, for example, humidity and all forcings, physical forcings that you have to add here as well, right? So this is the main goal. So it's a set of equations you want to solve on the sphere, right? So keep in mind that this is the goal. And now I'm going to go back about 100 years, and I'm going to do a history line where I'm going to show how we reach that goal. And with that, I hope to make a connection with HPC development and also motivate why MPAS. Okay, so that's why we're going 100 years back. And the history 100 years back starts with, well, is one of the main guys that worked on this is Richardson. And in 1922, he produced a book, which is really nice. It's Weather Prediction by Numerical Process, where he solved the primitive equation. So it's not yet, it's a hydrostatic assumption, right? So it has this assumption with respect to pressure and gravity. It was really marvelous forecast. It was a really interesting formulation from a mathematical point of view and from a meteorological point of view. Why was it so interesting? Well, one of the things he did, so he put Europe on a map and picked a latitude longitude grid, a rectangular grid, and set variables in what's called an E-grid, which is you position some variables in some places and other variables in other places. So it's what's called a staggered grid for CFD community, and approximately 200 kilometers of resolution each box, and use finite difference to solve the hydrostatic primitive equation. And then he spent several months of hand calculation. There was no computer at the time, in ambulance trips, because he was a driver at World War I, to derive the solution of this computation for a period of a few days ahead of the initial data he has. I think that's not, well, that was very interesting, but one of the things that he did, which I find interesting for this community, is that he's one of the first guys to think about what is a massively parallel computing system, even though there was no computer at the time. So what he thought was the following: let's get this grid on a building, an actual building, where you have each of these squares here representing one of these squares, and then you would have a center tower, and then you would have rooms here at the back, which will do maths and put numbers on here, and would pass information from one cell to another, and with chalkboards and things like that, would do computations and put here, and this would centralize all the calculations and coordinate what's going on. So this is pretty much how a cluster works, or HPC systems work, right? So you're doing computations in parallel, and there is some kind of central guidance to put in order and collect results and read data and things like that. So it's kind of interesting to see that 100 years ago, this was something along being developed. Well, at least idealized, right? We'll see how this goes in a minute when computers arrive. Okay, so a comment is that this forecast that he made did not work, right? So the actual forecast that he predicted was incredibly wrong. And the reason is that he didn't take into account several things related to multiscale nature of the atmosphere, right? So this was solved after 30 years or so only. And so there we had with again, thinking of HPC, we start with the first computer, well, one of the main first computers, which is the ENIAC. And one of the primary uses of this computer, the ENIAC, was exactly on weather prediction. So with this computer in the meteorological program of Princeton, they made the first numerical weather prediction, successful weather prediction, in the sense that they actually were able to calculate something useful, right? And so up until this, well, on this time and up until today, we can see that the history of numerical weather prediction is pretty much mixed with HPC. So when you see a new big computer coming out, sometimes it's related to big weather systems coming out as well. This is happening with European Center or the Met Office in the UK, or places like NCAR. It's always tightly related, the HPC and the numerical weather prediction developments, right? So for this simulation that they did in the 50s, they had to go back equations. So this was done with a barotropic vorticity equation, which is on that list that I showed in the beginning, is a simplified version. It's one of the simplest version of the equations, right? So in the 50s, we were going in the barotropic vorticity equation. And then we start moving forward on this. Well, several teams start producing like barotropic vorticity simulations. First operational forecast in Japan, in the US, in Sweden. And then in the 60s, we reached what was called the primitive equation, which was what Richardson had done in the 20s, right? Okay, because they realized that Richardson were doing something bad with the initialization of these models. And that's basically where climate change modeling also started. So you will see climate research, like climate modeling on gases and all the climate change thing happening, papers starting from the 60s. Okay? But that's where our history in terms of modern HPC starts and will guide us to understand what are the main new generation of models are, because some issues starting arising. Okay, so what they were thinking at the time was mainly we need to couple the whole globe. So we're thinking about using something like latitude, longitude coordinates, right? We start dealing with things like the pole problem. They started dealing with nonlinearity, so problems related with instabilities here. Data assimilation problems also start arising, and other things. I'm going to focus more on the HPC side of history here. So let's take a look at the first issue that arises, which is the issues that we're tackling today, okay, up until today at least. So the thing is that if you use traditional Eulerian finite differences, what happens is that the cells near the pole, they are very small. If you look here, they are like a very narrow in the x direction, right? So what it means is that because of CFL condition, you will have to use a small time step size here, right? So the pole is a limiting factor in terms of time step size. And the other thing is that if you put this on a big machine, you will have computational bottlenecks here at the pole, in the sense that this point will have to communicate with several other compute nodes. So you may have communication bottlenecks here. One of the solutions for this is to change your numerics formulation into something that allows larger time steps and avoid CFL. The way of doing that is if you use semi-Lagrangian. What does that mean? Is in the advection terms, you follow your Lagrangian path, so you follow the particles, you follow Lagrangian trajectories, but it's only semi. That means that you're regridding every time step, and semi-implicit, which means that you treat the faster gravity waves, which here in the atmosphere on the primitive equations, you have gravity waves, which are quite fast. And if you're on the Euler equation, on the compressible Euler equations, you have sound waves. So you really have limiting factors in terms of fast waves that you need to treat. So you treat these waves in an implicit fashion. So what happens then is that you can use a large time step, you have no pole problem, but then you have to solve a really large system at each time step, which may or may not be easy to do depending on your HPC system. So let's look at two examples on this. So one is the current operational UK Met Office production model, which is a non-hydrostatic deep atmosphere. It solves a global resolution of higher than 17 kilometers. It has a higher resolution, well, on top of the UK, and it's a really brilliant model in terms of competitiveness and accuracy and and results in terms of weather prediction, and also used for climate simulations. But then one of the issues that they are dealing with is that because of the large system that they have to solve, especially, they are reaching scalability limitations on this model, right? And here they use semi-Lagrange and semi-implicit. On a side, you have the WRF model, which I think part of this community is pretty familiar with. So the WRF model uses explicit finite difference on a C grid, which is you put the velocities on the edges of the cells and you put mass in the center of the cell. And the interesting thing is WRF is a really good model if you want to do it on a regional scale, because you don't have the pole problem. But then if you start trying to move towards a global model, which is what you would expect because of the global coupling of the atmosphere, you will start hitting this kind of problem, and you start hitting this kind of problem, particularly because WRF is an explicit finite difference scheme. So it becomes computationally unfeasible to run on large HPC systems. So these two models are reaching a giant bottleneck in terms of HPC. Okay, and then back in the 60s and 70s, people were already aware of this. One of the solutions that they came up with, which became what is now known as the state-of-the-art in terms of atmospheric modeling, is to use spherical harmonics and spectral calculations. So you write your fields in terms of spherical harmonics, which means that you expand them in Fourier and Legendre polynomials, right? And the interesting thing about this is that the Laplacian is well, these spherical harmonics are eigenfunctions of the Laplacians, which means that it's very easy to solve Helmholtz-like problems. So it becomes very easy to solve like implicit problems on this this basis. Okay, so this was a major revolution, and it allowed many places, really many places, to go operational on large scale with really state-of-the-art models. So, for example, the European model uses a global spectral model. The Brazilian operational center uses a global spectral model. The USA, up until 2019, used global spectral models, and many other places used spherical harmonics as the basic numerics for weather prediction. Right? This is more or less how the European center evolved in terms of resolution and how the model was historically evolving. Right. So at the moment they are running something like 7 kilometers, if I'm not mistaken, non-hydrostatic. It's a really full model, close to our goal in the first slide, right? So they are really reaching there. So then you say, well, things look good then, let's just use this. Well, this is not really the case. What's happening is, okay, we want to go higher and higher resolution, but then we need to do this, we need to run this in a really short time window. We need to run a weather forecasting simulation in 1 or 2 hours at most for a week forecast, right? And then the issue is, this is a little already old operational from our Brazilian operational center, our cluster from our operational center. It's already quite old. But then if you want to run it on a larger machine than this, particularly on a massively distributed memory parallel machine, if you use finite difference like in WRF, you will have pole communication bottleneck at the poles. If you want to use semi-implicit, you will need to solve a large linear system that usually is creating a global communication problem, and it's limiting the scalability of the models. And spectral transforms as well. So in order to do the transform from physical space to spectral space in spherical harmonics, you do need to have a global communication. And this global communication is what is limiting the scalability, for example, on the European Center model. So they are basically reaching the limit of scalability at the moment. So no matter how large the computer they buy, they will not be able to keep within this short time window if they want to go higher resolution. So that's the main issue. So how can we deal with that? And that's where the new generation of weather system appears, right? And this is where MPAS is going to come into play. So I hope this history more or less tells where we're heading. Okay, there are several solutions then. And these solutions mainly go through the point of avoiding a latitude-longitude grid or spherical harmonics and moving towards some more isotropic grids on the sphere. So you can either triangulate the sphere or this is a really nice formulation which uses a cube sphere. So you get a cube and you project the faces of the cube onto the sphere, and then you use logically rectangular cell. This is what the United States went for, right, with FV3. So the current operational model for the United States uses this. Or you can go more like a tennis ball, so this is like a volleyball. So you can go more to like a tennis ball, but then you have these overlapping regions which are really difficult to deal with. This is what Canada went for. The European Center is going to an octahedral formulation where you would get an octahedral, so 8 triangles face polyhedron, and then you put it with triangles. You put triangles in it. The interesting thing about this is that they can keep some spectral formulations, but then they reduce a little bit the pole problem. It's not that much. They still have some singularity here. So these are formulations that I'm not going to talk about. And what I'm going to focus on in the rest of my talk is on this, right? So the other formulation that we can go is to Voronoi-based grids. What's a Voronoi? Voronoi, then you put a set of points on the sphere, and a Voronoi cell is the cell that defines the region closer to that point to any other point. So if you have a point here, this hexagonal cell defines a region for this point. So it defines a region which is closer to this point than any other point on the sphere, right? So it defines this tessellation of the sphere, right? So usually you start off with a icosahedron, and it gives you a dodecahedron. So it gives you something like this. This will give you something like, if you imagine a football, right? Not the American football, the European football, Brazilian football. And you start working with that, and you start putting more cells. So you start putting more points, and then you get the resolution you want. This is the approach that went in Japan, and also in MPAS, and some other models in the United States went through this, right? And I think there's a German model on this as well. Okay, so we're going to go ahead and discuss this. And remember that the motivation for us to go in here is HPC. Okay, we want performance, and we want to beat what happens in the spectral models and what happens in latitude, longitude models, and models like WRF, right? So this is the motivation of going towards this slide. This is what we call the new generation of atmospheric models. Okay, so in this new generation of models, the two types of models that are gaining most popularity are those related to the cube sphere and triangular Voronoi grids. And there are 2 reasons here. You can either stick with the cube sphere to keep the logically rectangular shape, or you can go for triangular Voronoi because of flexible refinement, which I think is what interests a lot this community. Right? So this is what I'm going to focus in the remainder of my talk. So things that will attract wind energy community. Okay, and then there are 2 kinds of formulations that you would like to use in this. So when you go to these Voronoi grids, it's more attractive to use finite volume schemes. And then it depends on what you want to do with the finite volume, what kind of scheme you want. But typically you would want to use a finite volume scheme. And then on a cube sphere grid, it's more attractive to stick with finite element scheme, right? And so, but these new models, they challenge a lot from a HPC perspective. So is it really, are we really going to gain scalability with these new grids and new methods that are being developed, right? And then there's the bunch of well-known issues with HPC that you need to take into account. So we're going to build models from scratch. So most of these models were built from zero. So how can we build like already so the preliminary models were mostly built in Fortran 77, hand-coded things and hard to maintain. So how can we build something that already preserves some kind of easy to maintain and adequate for new architectures like GPUs and things like that, energy efficiency. So we have to keep this in mind, right? And I'm going to go into the line of finite volume and triangular Voronoi grids because I'm interested in MPAS, which is what motivates this talk. Okay, so for finite volumes, there are several things that we are concerned in terms of numerics. And the thing is that we need several properties. So it needs to be scalable, it needs to be accurate and stable, and you need conservation properties. These are particularly important for weather community. Okay, we need mass conservation, energy conservation, and we need good representation of waves. Otherwise, we start getting unphysical behaviors in the atmosphere. And I think this is valid for most of CFD, but for the atmosphere, this is particularly crucial, right? And we can get schemes like this that solve almost all of this, except scalable, for latitude, longitude grids. So, for example, the WRF model has most of these properties. But then when you go global, which is something that you would like to do, you reach scalability limitations. So how do you go to a grid like used in MPAS and to gain scalability and still preserve these properties? And that's a major issue, right? So let's go into MPAS. So this issue was partially solved in this paper of 2010 by Todd Ringler, Thurburn, Klemp, and Skemerak. John Thurburn was my postdoc supervisor. So I worked a lot in this kind of formulation. And then 2012, that's where MPAS, the official paper from MPAS came around. And what they do to keep those properties is use what's called a staggered grid, but it's a kind of a nasty staggered grid in the sense that you keep the velocities, but only the normal components of the velocities in these Voronoi cells. So the velocities are on the edges, and then the mass pressure is on the center of the cells. And you will have this duality where you have a Voronoi cell where you keep the mass, and then your vorticity terms will live here on these triangles. So there's a big interplay on how you deal with all the numerics and how you deal with velocities. Because note here that you only have incomplete information on the velocity. Okay. Okay, so this is a really quick introduction on MPAS, and it's a full 3D model for the atmosphere, which allows great flexibility on grid. It solves the non-hydrostatic, so we're almost on the top of that list of equations. So it's reaching our goal, right, of solving the compressible Euler equations. And the only thing left now is, well, at the moment they built this, was dealing with the numerics, coming up with decent numerics. And this paper was one of the main solutions. Was it the main solution? Well, several interesting things start happening. And now it comes to my more part of the talk where I discuss some issues that will arise in MPAS. And if you note these in your simulations, you should be aware of these issues so that if you notice these on your simulations, you know where they're coming from. And one of the interesting things is that dealing with these grids is non-trivial. So if you get a solid body rotation field, so that means that the velocity is simply rotating. It's a simple rotating field. And you just calculate the divergence as this method that used in MPAS does, what happens is that the error which you see in your field, you can basically see your grid. So this is a more or less high resolution grid. So you have small cells here, but you can basically see properties of the coarse grid, right? So this is called grid imprinting. So a lot of the times when you do simulations with MPAS, you will notice some kind of grid imprinting, which means that some places in your simulation will give errors which are unexpectedly high, and it's nothing to do with the physics, it's only to do with the grid, right? So this is something to be aware of. It's called a grid imprinting. There's some further information. I'm always giving references here, so I think this presentation can be sent later if you want to take a look at the references. The other issue, which I think is quite important for the wind energy community, is how to deal with this, well, the MPAS winds. So the MPAS wind it looks like this on this picture. So you only have incomplete information. So here you only have the wind, the normal component of wind in this direction with respect to this edge. So you don't know anywhere on the grid the full velocity. So you have to reconstruct this. And one of the issues is that reconstructing this is although it seems easy, it's kind of a nasty trick. And then MPAS uses what's called a radio basis function to do this reconstruction, and it uses this RB6. And the issue with RB6 is that depending on how you use it, you may get stuck in resolution. So what does that mean? So if you increase your resolution, like you go to a 3-kilometer grid, the error you will observe in this reconstruction is constant. So you can't expect better reconstruction of wind. And what it means is that if you have a constant wind, this kind of reconstruction will not reconstruct a constant wind, right? So you will have minor errors on your, not necessarily minor depending on what you're dealing with, but you will have errors on representing wind in a very local scale, which is something important for wind energy. But there are several alternatives to deal with that. So the current MPAS implementation, I think, uses RB6, but you have solutions to that, right? So you can implement your own interpolation scheme to reconstruct your vectors for your purpose of wind energy. So this is something I think should be pursued from the wind energy community. And then the other thing that happens, which is a major issue that I think people from MPAS are kind of avoiding it because there was no, the solutions to solve this are not yet ready, which is for some reason, as you increase resolution on MPAS, so this is resolution, right? So if the G level is the level of refinement that you go, and if you increase resolution with MPAS, what happens is if you put an analytic field, so some flow that you know the analytical solution, it won't converge, right? It's said to be 0th order accurate in terms of convergence. And this is kind of, from a numerical analyst perspective, this is not really nice. So this is an example for shallow water equations on the sphere, which is a simplified model of MPAS, but it uses exactly the same numerics, right? So the red line is what MPAS happens. So this is the truncation error. So this is the consistency error, right? And then, for example, the momentum equations is 0th order, right? In the root mean square error, and it can go -1 order here. So I built my version of MPAS, which is this MPAS PXT with more accurate operators. So there you can go up until this blue curve. So you do get convergence. There is an unexpected issue with stability that you get here. So you need to add more diffusion to control stability. So you gain accuracy and you lose a little bit stability. So there's always a duality on these finite volume schemes, low order finite volume schemes, where you want to preserve some mimetic properties that you have to deal with. Okay, so this is an issue that you need to be aware of. That the theory says that going higher resolution with MPAS does not necessarily gives you better solutions. In practice, this hasn't been seen to be a big issue, but there is this theoretical downside. And MPAS suffers from this instability, which is called Hollingsworth instability, which is mostly related to nonlinearities and the way they treat the nonlinear terms. So the advection term in MPAS is treated as decomposed and kinetic energy and vorticity terms. And there's a cancelling effect that is not mitigated in a model. And then you start getting these instabilities. So that's one of the reasons that MPAS requires quite a lot of diffusion. So you should be aware as well on how much diffusion you would need on your, well, how much the artificial numerical diffusion may affect your wind energy model, which well, is basically is going to deal with turbulence. So so you have to be aware that the numerics of MPAS is extracting energy that might be of interest for the wind energy model. Okay, so now let's take a look a little bit on the history of MPAS on the past few years, right? So in 2014-16, there was this high impact weather prediction project, which made an assessment of the future operational weather forecast for the USA. And so they picked 5 models and they tested a lot all these 5 models. One of them was MPAS, the other was FP3, which became the operational model. And all of them uses these new grids, so mostly cubed sphere grid, cubed sphere grid, cubed sphere grid, cubed sphere grid, and this uses a Voronoi grid. And one of the things that I want you to notice, this is a 3D test, which should be all 0 here. This is only error. And if you see here on the FP3, you can see a cube, like corners of a cube. This is grid imprinting for the cube sphere. And then MPAS, you see like a wave number 5 or 6 grid imprinting as well, right? And in the other models, you also see this. So it's very common when you run MPAS, you see this kind of oscillations, which are purely numeric. This is non-physical, okay? And then what happened is in this project on the decision, MPAS was still not mature enough. And it ended up losing in terms of performance, computational performance. So the red bars are the time, well, number of cores required for certain simulation for MPAS, and you can see that it's way higher than the green one, which is FP3, right? So they didn't consider MPAS further, but then MPAS was still very immature, and it now has gone through major computational improves, and I think it now would be really more, well, closer to competitive with FP3. And there's some recent advances on MPAS on GPUs, and this is something that we've been discussing here in Brazil, because we are considering MPAS as the next generation weather forecasting system for Brazil. And NVIDIA, with this big effort with IBM and University of Wyoming, they did this development effort where they ported all this big chunk of MPAS, all physics, dynamical core, which is mainly the part where the Euler equations are, microphysics, boundary layer, drag wave, and things like that. And they ported all this to GPU, right? And it works really well. We did some experiments on this, and well, we've discussed with NVIDIA a lot of experiments on this, and they've run simulations on like a 15 to 3 kilometer grid, and with very small execution times. And I see that I have well, about 3 minutes, 5 minutes. I'll just head towards the end here. Okay. So
if you can just wrap it up, not to, I mean, I know we started late, but just to give you some minutes now for conclusions.
Okay, so, and then, so it worked really well on GPUs. I think that's the main thing. And then I'll just show a couple of slides on advertising a little bit of things for wind energy. So there's been quite an effort from the DTU and Edinburgh APCC Center on, well, doing experiments with MPAS and WRF towards seeing how the performance of this looks. So thanks, Mark, for this. I think if you want to chat with them, if you're interested on this. And then the other thing that is interesting is what kind of grids are adequate for wind energy. So Marta from Vortex has been working on her master project and developing, trying to work out grids, and it's very complicated. You can get these nasty grids here. But I mean, well, at least here in Brazil, we are dealing with grids that can handle strange things, and we are regenerating very high quality grids. So I hope we can solve this for wind energy. And as a last slide, if you want to look into, well, the effects of high resolution solutions from MPAS on a locally refined grid, which goes up to 3 kilometers, take a look at this paper. Okay, it's really nice. And this is one of the results where they show, well, the actual wind field. And the bottom line here is just be careful that MPAS may be a little bit diffusive. I mean, the winds that it's passing through is a little bit smaller amplitude than you might get in WRF or you would get in real data. So just be aware of that. So this is just some general thoughts that we can discuss. With that, I'd like to end my talk so that we leave some time for questions and discussions.